Well, let's call this point P. Oops. Let's call this point P. And then before we still have X and Y, X-axis, Y-axis, we still have that. And the P has X value, has Y value, right? So we could write down P like this. P is a point, has X value, let's call A, has a Y value, let's call B, right? So we describe P as a point. Now, with a vector, we want to enhance this point idea. So what do? We'll connect this point with the origin. It doesn't have to be with the origin, but for now, let me connect it with the point, a special point, the origin. Then I give it an arrow. I add arrow to it. I said, I add arrow at the P. So now what I have initial point. Let me write it here. Initial point. Which I'm going to call O. O means the origin. I put the O here. That's not 0, okay? That's letter O for the origin. So my initial point is the origin O. Let me write down that. And what is O is a point, right? What's its value? X value is 0. Y value is 0. Right? And my endpoint, how do I know that P is my endpoint? Because I put an arrow on top of this P. So I call that one endpoint. So P is my endpoint, which is A, comma B. So how do I say OP as a vector? So I have OP equals to the endpoint subtract initial point respectively, okay, with X subtract X, Y subtract Y. So endpoint subtract initial point. How do we do point subtraction? That sounds weird, right? We subtract component-wise. So what's endpoint? Endpoint is A, comma B. What's the initial point? Initial point is 0, comma 0. So how do we subtract these 2 points? So this is new. For this class, yes, we can subtract points now. So how do we subtract? We subtract component-wise. So the first one, the endpoint A, comma B, the first component is A, second component is B. Initial point, first component is 0, second component is 0. So we call the X value first component, the Y value second component. So we're going to do this. We keep this parentheses. We say, okay, A minus 0. Then we put a comma here. Put a comma here. This is the confusing part, but I'm not going to explain more. B minus 0. Then let's do a subtraction, because in each component, that's just real value subtraction. I know how to do that, right? A minus 0, that's just A. B minus 0, that's just B. So this is the confusing part. This the parentheses A comma B, that looks just like a point, right? That looks just like a point. So, but from now on, since we're in the vector world now, we're going to use this. But if this is too confusing, we have a second part. We're going to use this notation. Okay. If you think, okay, this just doesn't make sense, it's so confusing. So what do? We do this. We do A, we put the I behind him. Then we do plus E, we put a J behind him. Right? So here we call I first component. Component is a word. Component. Right? So remember that's X value. J, second component. Y value. Okay. So once we get used to it, we can go back to this, parentheses, A comma B, parentheses. All right. So what does this mean? This means, so now before the point, so a point A comma B before now is a vector with initial point of the origin and endpoint A comma B. It's almost like a, okay. So in this we see a point A comma B, same as the vector A comma B, right? So what we can remember from this, any point is a vector, can be seen as a vector come out of the origin to the endpoint, right? So what do I mean by this? So P now gets a new perspective, right? P before is a point, A comma B. Now for our class, we want to see P as a vector, is come off from the origin, is this line segment, come off from the origin and end at point P. Anyone has any questions so far? Okay, remember this. As said, what is the vector? We subtract 2 points, right? We subtract 2 points. So now, if I have another point, let's say I have a point here. And I call it Q. I call it Q. And because Q is a point, maybe I can say Q equals to C comma D. Right? Then I connect those two. So from P to Q, I can connect those two. Okay, a vector has direction. So the idea of vector has a direction. So depending on which point I consider as the initial point, or maybe let's call P initial point for PQ, right? So if I write down like this, PQ, that means P is initial point, Q is endpoint. So P is A comma B, and the Q is C comma D. By convention, the first letter is initial point. The second letter is the endpoint. So in this case, I got a vector. I got A minus C in the X value. I got B minus D for the Y value. So PQ represents this vector. Starting from P, end at Q with an arrow on Q, because Q is end point. And again, we see this A minus C, B minus D looks like a point, right? And it is a point. Can anybody think which point this represents? A minus C, comma, B minus D, by using this? Yes, it's PQ. But can we equalize this with one point? Oh, you mean PQ point? PQ. But PQ is not a point, right? You see, P is at one place, Q is at one place. It's just the point A minus C, B minus D. If we want to draw it, we have to draw this way. So we parallel. So this is called a parallel translation, which means we make one okay. So we translate the PQ vector to this O something. Let's call this Q prime. Q prime. So A minus C, comma, B minus D is a point Q prime. Q prime. This is called a parallel translation. So for any vector in space, we can always push back to the origin. All right. We can always push back to the origin. We can push back P to the origin. We also can, maybe we want to push Q back to the origin. But because this arrow is on Q, right? Preferably we push P back to origin. And this is the picture of it. You see, we have pushed P to O. We have pushed Q to Q prime. So now parenthesis A minus C, comma, B minus D, close parenthesis, becomes the point of Q prime, or becomes a vector of OQ prime. Does it make sense? Yeah, Q is the initial point, but we have pushed. Parallel translation is legal. It's good. We always do parallel translation in vector space. Because sometimes, this is only 2 space. Imagine we get into 3 space, 4 space. Imagine the vectors are flowing in the air. Think about today's weather. Well, I'm in China. We have different weather now. Think about the wind is blowing, right? We could use mathematics. We could use the idea of vector to describe the field of the wind blowing. So there are infinitely many vectors going on. So when the wind blowing, the infinitely many vectors are flowing around. And how do we study these vectors? We want to push back one of its initial point or endpoint back to the origin to study. Parallel translation, yes, that's it. Parallel translation. So with a vector space, parallel translation is allowed, and then you don't have to pay anything for it. Right? Mathematics, sometimes we want to change one thing to another, we have to pay price. But for vector space, we don't have, it's free. We don't have to pay for it. So which means PQ vector and OQ prime vector are exactly the same. We treat them exactly the same. And it's a lot easier to talk about OQ prime than PQ, because PQ is in space, right? It's in space. It's hanging there somewhere. And we drag them down on Earth. So O, starts from the P starts from the origin O. All right, so same idea, we can go on higher dimensions, right? We can go on higher dimensions. I'm going to draw, okay, let's see, we still have, this is our Z x-axis. I'm going to draw Y x-axis and the x-axis. Okay, let's see, this is the X. There are different ways of drawing. Okay, you can draw your own way. But just imagine corner of your room. Okay, now you're sitting in the room. You see the corner. You look at you look at the one corner of your room. There will be just one quadrant of this three-dimension, Euclidean three space, or R3. We call this one R2. Euclidean two space. What does it mean? It means R cross R. It means we have a R cross R. What does cross mean? Okay, so we have a x-axis as a real number 9. We have a y-axis and another number 9. And those two number lines are perpendicular. All right, so this cross here means those two real lines are perpendicular to each other, which means they're making 90 degrees. Here, same thing, three space, Euclidean three space, we call R3. You see how I wrote my R? When I'm, use it as Euclidean space, that's just by convention. I double these vertical lines. I double these vertical lines for R. So R3, which means R cross R cross R. So we have Z and Y perpendicular to each other. We have XY perpendicular to each other. We have XZ perpendicular to each other. All right, you can use your arm also. You can use arm. Well, that's only two dimension, right? Look at the corner of your room, right? This is one quadrant of it. So if I have a point somewhere in the space, so I would have X, Y, Z value, right? So this point I would have, well, let's use some other, because I use X for X axis, or maybe I use X1, Y1, Y1, Z1, right? Because I'm in a three-dimensional world. I have X value, I have X1 value for X, I have Y1 value for Y axis, I have Z1 value for Z X axis. So this is a point, but once I connect with the origin, it becomes a vector. It becomes a vector. And then when I put an arrow on it, and by convention again, usually, we let the vector start from the origin. So very origin is the initial point. And this head is endpoint. So now I look at this vector. So this vector has a length, has 2 points, it's connecting 2 points. It's a line segment. It has an arrow, shows me direction, shows me from which point go to which point. Anyone has any questions? So on and so forth. Because vector is such a beautiful idea, and there's no limitation about talking about Euclidean n space. As long as n is a finite number, it's not an infinity sign. We can talk about n equals 25. That means Euclidean space of 25 dimensions. All right, so that's the beauty of it. So we can talk about 2 space, 3 space, keeps going on. Things works, so we use this vector idea. Right? So a vector can survive in first dimension, in second dimension, in third dimension, in 25th dimensions. What if we are given a vector that doesn't start at the origin? Do we have to manipulate the vector? Depends on the situation. Depends on the situation. Sometimes we can directly deal with it. Sometimes we need to push back. So later on, when we talk about differentiation, something called directed derivatives, we have to, for that case, we have to always push back the vectors in space back to origin. We always do parallel translation. All right, so it depends. But for now, how much of the vector idea we're going to use for the rest of the course, that's another story. But for now, we want to learn the space of vectors, to use a vector to measure stuff. If you think about to use vector to measure stuff, so what do we mean by that? Think about this 3-dimension, right? I have x1, y1, z1. So how do I connect that with my life? Let's just use this example. As I said before, right? So maybe x-axis measures human's weight. Maybe y-axis measures a human's height. And maybe z-axis measures, how many language one person speaks. So I have these 3-dimension recordings. And we call it a vector. But each one is a real number. Each one is a real number. So anything we can do with real number, we can do with vectors. But not anything. Let me take that back. So some of the things we can do with real numbers, we can apply to vectors. Let's see what can we do with vectors. So I have to go to another page. I have to erase this, I guess. If anyone wants to take a picture now. I need to get a new one to talk more about vectors. Any questions? Okay, let me get another page. Oh, it doesn't. Do I have to erase? This is no good. So before, they just changed something. Before, I can keep going on the same page. No, I cannot. I have to erase this, I guess. Okay, so now let's see. Okay, so now let's see. I have vector P. Maybe it's 0, 1. Maybe let me use A1, B1, C1. Okay, we can talk about 3 dimensions or 2 dimensions. Preferably, let's talk about 3 dimensions because we live in 3-dimension space. I may have A2, B2, C2. Right, so I have these 2 vectors. So what can I do with these 2 vectors? I know we can look at the P as one point, right, which has x value A1, y value B1, z value C1. And we can look at P as a vector come off from origin. Right? It's a line segment. So I have 2 ways of looking at this P. Same thing for Q. So we have something called a vector addition. We add component-wise. or subtract, add or subtract, right? When we add a negative number, let's subtract component-wise as we did before. So let's see, how do we do this? If we want to Q minus P or Q plus P, we can add two vectors. So how do we add them? We add component-wise. That means A1 plus A2, B1 plus B2, C1 plus C2. So this operation is component-wise. Values on x-axis can be added together. Values on y-axis can be added together. Values on z-axis can be added together. So this is adding two vectors. And this adding has geometric meanings. Let's say I have three space. Right? I have Q, I have P. I want to change the color. So please don't use whiteboard to present, okay? It takes too much time. Okay, just pretend I have this P, I have this Q. So P, we can look at it as a vector from the origin same thing for P, for Q. I want to look at this. We need to add an arrow. So this, I'm still call this O. So we have vector OP, right? The value is same as the point of P. We have OQ. And then we can form a parallelogram. I'm going to, it's like a copy. I'm not going to translate, parallel translate the OQ. I'm going to copy OQ and paste it right here. Right? I can call this OPQ prime. Right? PQ prime. Then I can connect Q prime and Q. So I have made a parallelogram. Just trust this is parallelogram, right? But it's off, of course. My joint is off. So what is the geometric meaning of Q plus P or OP plus OQ? It's the diagonal, the longer side of the diagonal of this parallelogram. Let me change another color. So it's from O to Q prime. And with the arrow on Q prime. Right. So P plus Q or OP plus OQ equals to OQ prime. And why can I? Q, yeah, a Q prime. Or just a Q prime point. So this is the geometric meaning of when we add two vectors. So two vectors, if they're not collinear, collinear means those two vectors fall on the same line, means those two vectors are parallel together, are parallel. If they're parallel, if two vectors are parallel, we can do the parallel translation for free. So that means those two vectors fall on the same one, we call collinear. So if two vectors are not non-collinear, they always form a parallelogram. And the longer side of the long side of diagonal is the addition. And the same way the short side is a subtraction. Okay, let's go to the color again, yellow. So this one will be subtraction, right? Depends on arrow, you know. Depends on the arrow, it could be P subtract Q, or it could be Q subtract P. So that's the geometric meaning of adding two vectors or subtracting two vectors. And we cannot multiply two vectors, but we have something called dot product. And it has another name, inner product. You have, oh no, what is that? What if we're given a vector that doesn't start at origin? Do we have to manipulate the vector? It depends. Sometimes we have to. Sometimes, like later on, we're going to talk about directed derivatives, stuff like that. We have to do parallel translation first, then take the derivative. But not all the time. What did you see vector had to be in order to form a parallelogram? Oh, non-collinear. Collinear means, I'm typing in the chat. Collinear means two vectors are parallel. Okay. When P subtract Q, we define the vector as PQ. Yeah, the first one is always the initial point. The second one is the endpoint. Right? PQ, the arrow will fall on Q. QP, the arrow will fall on P. PQ, initial point is P, endpoint is Q. QP, initial point is the first one, is Q. P is the endpoint. The arrow always fall on the endpoint. You're welcome. Okay, so we can do something called a dot product. Let's say here we have PQ, right? So we do P dot. I use this symbol for dot product. P dot Q equals to P is A1, B1, C1 dot A2, B2, C2. So how do we dot product? Anyone wants to make a brief guess? So we know we add component wisely, we subtract component wisely. What's your suggestion? If we dot product, so basically this is multiplication. We have two kinds of multiplications of vectors. So we would multiply component-wise. Great. Multiplying component-wise. Yes. That's exactly what we do. So A1 times A2, comma, B1 times B2, comma, C1 times C2, comma. Yes, someone has mentioned cross product. So this is dot product. dot product, we dot product component wise. And again, 妈，好多蚊子，我这腰都受不了了。Again, going backwards, someone may think this is confusing. How do I write a vector differently? We can write a vector as a1i plus b1j plus c1z, right? Because in Euclidean space, we have x, y, z, and later on when we go higher dimensions, sorry, I want to move this one to the first line. Oh, yes, I did. We still, just by convention, I mean, of course, you can call them any names. So, but later on, if we go to a higher dimension, we extend it to the n dimension, we will see x1, x2, x3, instead of seeing x, y, z, right? So I actually is a vector. J is in a vector. Oh, not z, I'm so sorry. K. K. All right, so we use I, J, K. I, J, K are vectors. Let me show you where are I, J, K hiding. Let's use black color. So I is on x-axis. So let's call this x-axis. Let's call this one y-axis. Let's call this one z-axis. So I is this guy. So this number is 1. And I is from the origin on x-axis, starting the initial point is the origin, and the endpoint is number 1, value 1. So so what's I? I itself is a vector, has a value 1 in x-axis. What value in y-axis? What value in z-axis? 0. Because I is just one part on x-axis. So its first component represents x value, which is 1. It has no value on y, has no value on z. So I is a vector 1, 0, 0. Similarly, y, let's see, this is positive. It's a vector here. So can anybody tell me what's the value of j, not j, not y? J equals to, yes. So x value is 0, y value is 1, and z value is 0. So j is a vector. What about k? Can anybody think about k should be? K is a vector. Yes. Yes, 0, 0, 1. Awesome. So 3 vectors. So now let's go back to the new notation. What is A1I? What is B1J? What is C1K? Let's just write them out. So that equals to A1 multiplied by I, but I is a vector, is 1, 0, 0. Then plus B1 multiplied by J. J is 0, 1, 0. Then plus C1 multiplied by 0, 0, 1. Right. So let's look at A1 multiplied by a vector. So I is a vector. So we call this scalar multiplication because A1 is a number. A1 is a real number. 1, 0, 0 is a vector. We can always do that. And this is called a scalar multiplication. So basically we have three kinds of multiplication involves vectors, right? We have dot product, the one multiplication. We have this scalar multiplication, which is a number, a real number multiplied by a vector. It increases, or it tries to increase every component, right, by this scalar times. Then what is this? So I'm going to write here. So equals, so a1 times 1, that's just a1. a1 times 0 is 0. a1 times 0 is 0 again. So a1 times 1 comma 0, 0, 0, or a1i is just, the first component is a1, second and the third component is 0. Then plus, this is so difficult. That's why I said don't use this to do presentation, okay? Oh, why is always copies? I just, oh, maybe because my hands are there. Okay, now plus. When we use IJK notation, always plus, unless the number is negative. Then B1 times 0, comma 1, comma 0, that becomes 0, B1, comma 0, right? Maybe I put it back here to make it more obvious. So I have A1 times 1, comma 0, 0. That's a scalar multiplication. I get an A1, comma 0, 0. B1 times 0, comma 1, comma 0. I get a 0, B1, 0. And C1 times 0, 0, 1. Same way. Plus 0, 0, 0, C1. So that's my 3 scalar multiplication. Now I have 3 vectors. I have A1, comma 0, 0. I have this vector, and this vector, and this vector. How can we do with the additional vectors? We add component-wise. So when we add A1 plus 0, we still get A1. We plus 0 to B1 plus 0 again, we still get B1. 0 plus 0 plus C1, that's C1. Okay, so this shows us why those two notations are equalized, right? So why this one equals to this is through here. Let me know if you have any questions. I got many mosquito bites. So there's 2 kinds of multiplication with vectors, involved vectors. We have the other one. The other one called cross product. Cross product. So let's see, how do we cross product P cross Q? We want to calculate this. This we use IJK all the time. First, we put a long bar. Oh, these colors. Long bar here. Then we'll put out another long bar. Then we put IJK in place. First row I, and the first row, first column I, second column J, third column K. Then we have the values, component values for P. We have component values for Q. We're going to put because it's P cross Q, so we're gonna put the components of P first. Under I, under J, under K. So P is A1, A2, A3, that's vector P. Then Q, the last row, the third row, A2, oh no. Sometimes we do use A1, A2, A3 this way, but for this now, I use B1, right? I use A1, B1, C1. I should stay with that. So that's C1. Then the third one is A2, B2, and C2. Sorry. B2, B2. Okay, so first I write this way. This is not so good. Let me move the bar a little bit. So I put a bar on both sides to indicate this is cross product. Cross product of two vectors. And this is very important. Later on, we're going to use this because we're going to calculate something called a determinant. Determinant. But if some of you have learned linear algebra, you may know this already. So we put two big long bar on the side. We put the ijk on top. Then we put the values of first vector, a1, b1, c1. Then we put the vectors of q on the bottom, a2, b2, c2. Now what do we do? Now let's write the equal sign here. So let's see how do we do this cross multiplication, cross product. So equal to, now let's write an I. We can write an I up front or I behind this. What is this? We're also going to make bar, but this bar is a little bit shorter because it only has 4 members. The first one, we have 3 by 3, 9 members. But now we have only 4 members, 2 by 2. So I'm going to make the bar first and then tell you where do we draw these 4 members. So this will be our first part. Totally we'll have 3 parts. Then the second one, we're going to write down minus j, minus j. We're going to do the same thing. Minus j, minus j. We're going to do the same thing. Make this bar. This bar inside also has 4 members. Then we're going to add the k part. 3 components, right? So cross product is still, oh, I made some mistakes. Oh my goodness. Okay, let's hold on this thought. I have made a huge mistake. Inner product, that product is a number. It's not a vector. I made a huge mistake. So we do multiply component wisely, but then we do not form a vector. What do we form? We add them. We add them so they become a real number. This is super important. Okay. You see, A1 is a number, A2 is a number multiplied by number is a number, B1, B2 numbers, number multiply, C1, C2 numbers. So we add 3 numbers, we get a number. So make sure you remember this. Is a number, all right? That product, inner product is a number. But the cross product is a vector. another vector. So P is a vector, Q is a vector, so P cross Q is another vector. And this vector also has a geometric meaning, which is perpendicular to P and perpendicular to Q. But let's leave that for later. So it's a vector. A vector has 3 parts, right? It has 3 components. Because P has 3 components, Q has 3 components. P cross Q is a vector, has 3 components: I component, J component, and K component. But where do we draw these 3 components? So let's write down I, J, K first. So K multiplied by I. I put 2 bar and the 4 members here inside. So I as a component is positive. I will explain to you why negative J, why positive K. The answer to scalar multiplication is a vector. Yes. Yes. Scalar multiplication is a vector. Yes. Yeah, right. It just increases the scale, the vectors. It is a vector. So let me change my color. I'm going to change to be this color. So when I do I component, okay, so I'm going to think, ignore this column, ignore this row. I'm going to take B1, C1, B2, C2. You're welcome. You're welcome. So to calculate the I component, we put B1, C1 inside this bar. B2, C2 inside this. And then I will explain to you something called determinant. Okay, but for now, we just draw this. So for the I component, I'm thinking cross the column, cross the row, right, of I. I'm taking the remaining ones. So the remaining ones are B1, C1, B2, C2. I put it inside this bar. For the J component, I'm going to do the same thing. I'm going to ignore J row and J column. So what I'm left with? I'm left with A1, C1, A2, C2, 4 members. Hey, I'm going to do the same thing. I ignore the row and the column with K. So what I'm left with? I'm left with A1, A2, B1, B2. Okay, so I have this now. And something called determinant. Determinant. It's just a mathematical form. What does that mean? That means my I component, so the 2 bar and 4 members inside, how do I calculate? I calculate B1 multiplied by C2. B1 multiplied by C2, subtract B2 multiplied by C1. You see, I multiply them diagonally, then subtract them. So I'm going to this one first, subtract this one. B1, B2, so this is called a determinant. Determinant is defined based on 2 by 2 matrix. Determinant. 2 by 2 matrix. What do I mean by matrix? So you see, when I put, I'm going to do this. Matrix we use this sign. We use this bracket. So we put an entrance, maybe A1, B1, A2, B2. So this is a matrix. A real number is a matrix. Right? How many dimensions? How many rows? A real number has 1. How many rows? 1. So a number is 1 by 1 matrix. And this is a 2 by 2 matrix. So the 1, 1 position, so first row, first column is A1. And the 1, 2 position, first row, second column is B1. 2, 1 position, the second row, first column is A2. 2, 2 position, the second row, second column is B2. Is it possible K is supposed to be A1, B1 on top? Thank you. I wrote it wrong. Because sometimes I use, you know, I do A1, A2, A3 for vector for B1, B2, B3. Yes. Thank you so much. This is wrong. Thank you for catching that. This should be B1. This should be A2. Oops. A2, B2. Thank you. I have to be consistent, right? But later on, if you take a matrix class, right, they're offered by 1. But anyway, offered by negative sign. Yeah, so I did it wrong, right? I made a mistake. Is a 1 times B1, oh, I times B1, C2, B1, C2, subtract B2, C1. Oh, yeah, oh my goodness. Oh, yeah, this one is right. B1, C1, B2, C2. Yes, that's right. B2, C1 at the bottom of the page. For yes, you're right. Oh, did I read it wrong? B1, C2, subtract B2, C1. Yes, I read it wrong. But I wrote it same as yours of the page for calculating the determinant. You're right. Yes. So that's the determinant of this. So you are exactly right. So this guy is a determinant. This guy is a determinant. And this guy is a determinant. So now let's calculate the rest. So the I component is this. Then, so J component. So I'm going to explain to you why J component is negative. So let's write the determinant for the second matrix. So we get an A1. Oops. A1, C2, subtract A2, C1. Plus K component. So what is K component? The determinant for this one is A1, B2, subtract A2, B1. Okay, so this is one I component. Why I wrote 1 here? This is I component. We have I, J, K components. So why J is negative? Why J is negative? And the I and K are positive. Let's see A1. Let's use A1, B1, A2, B2 as example. So A1 is a 1, 1 position. So the first one is the row number of A1. So A1 is at the first row. The second one is the column. So A1 is at the first row and first column. So its position is 1, 1. And 1 plus 1 is 2, even number. Even number indicates positive. Well, let's see B1. B1 is in the position of 1 and 2. 1 plus 2, odd number, indicates negative. So on and so forth. All right. So what's the A2? A2 is 2, 1. 2 plus 1, odd, negative. B2. So on and so forth. So now let's see I, J, K, 3 components, right? So what is the position of I? First row, first column. First row, first column. Right? So 1 plus 1, even number. even number. So that indicates I component here. If we put I here, I gets positive. And later on, I'm so sorry. I'm at home, so my mom and my brother going in and out. I'm trying to keep them away. So later on, when we calculate the determinant for 3 by 3 matrix, we can pick any row, any column to work with. But the rule is this. It depends on if it's positive, it's negative. It depends on its position. So 1 position, I positive. J is 1 plus 2, right? First row, second column, 1 plus 2, odd number. Odd number indicates negative, so negative J. K is the first row, third column, 1 plus 3, even number, indicates positive. So that's how we get a negative J. All right, so now that's it. You see, P cross K is non-vector. And the vector, the first component is B1C2 minus B2C1. If we're given some numbers, this will we calculate, we'll get a number. And the J component, right? Well, of course, we get, what do we get? J component actually is A2C1 minus A1C2, right? Because we have negative sign in front of J. And we can push this negative sign inside the calculation. We will get A2C1 minus A1C2. For K component, we get A1B2 minus A2B1. Right? Okay, you have 5 more minutes, but we have covered a lot. Now let's go back to the textbook so you know where to read. Let's go back to the textbook. So this picture shows you the vector and a point can be looked at as a vector at this line segment. And it's in 2 dimensions in R2. We see this is 3 dimensions, right? X-axis, Y-axis, Z-axis. Right? We see this. So geometric representation of the point 2, 4, 4. You see this point 2, 4, 4. If we connect this point with the origin, we will see a line segment, right? It can be seen as a vector. The real number line is called space 1, R1, or simplified, just R. Just ignore the 1. So we call 1 space. The set of all ordered pairs. Ordered pairs is a fancy name for points of real numbers. It's called R2, 2 space. Right? 3 space, so on and so forth. So I have Rn space. N space. So the idea of vector can go to finite many space. It cannot be R raised by infinity. Okay, we don't deal with that. Vector space has to be finite many, has to be a finite number of the dimension. We do addition, scalar multiplication, of course subtraction, right? Scalar multiplication. If we multiply 2 numbers, right, we can switch those 2 numbers. Alpha is a number, beta is a number, A1, A2, A3 is not vector. We can multiply alpha first to A1, A2, A3, or we can multiply beta to A1, A2, A3 first. Order doesn't matter if we have 2 scalars. If we have plus 2 scalars, we can split into this. Right? Scalar with alpha, then plus scalar with beta. If we have a scalar applied to addition of 2 vectors, we can apply to each, then add them. Distributive, right? alpha multiplied by the origin is a point, and also can be seen as a vector, right? It's still the origin. 0 kills any vector, right? If we multiply 0 with any vector, that kills vector to the origin. Basically, you think about A1, A2, A3, right? It's not vector. What does 0 do? 0 just push it back to the origin. 1 doesn't do anything to the vectors because 1 is just 1, identity, doesn't change. The little proofs of each. So this tells us, we can add two vectors. We have vector A, vector B. A plus B is this. A minus B or B minus A depends. It would be a shorter diagonal. The direction depends on if it's A minus B or B minus A. This just use another notation, right? Look at this. When the birds fly, what does the bird do? Actually, it just creates a vector field, right? Creates a vector field. The idea of vector was invented, it was very powerful. We can always translate a vector, right? Be translated to the origin. This shows us why vector A plus vector B is this long diagonal. You see right here, right? If we have A, so plus B, this shows this. So this is formal definition of vectors, right? Make sure you read this, you go along. For this book, the bold letters represent the non-vector, right? The regular one writes numbers. So make sure you see this A represents a vector. Those are representing numbers. This is a picture, if we have this vector A, if we multiply by a quarter, so we shrink quarter. If we put a negative quarter, it goes to the other side. So you see the head, the direction gets changed because the negative changes the direction to opposite. Right, so this is B minus A, right? You could try A minus B. Right. You see, this tells you, okay, you add two vectors, then you multiply by scalar vector, then you draw the picture. Okay, tonight you have a homework like this. Ask you to sketch this, given your vector. Standard basis. So I, J, K are called standard basis, and each one is a vector. We call unit standard vector. Standard unit vector. So picture this, right? So this is the I, this is J, this is the K. So that's why vector A can be written as A1I, A2J plus A3K. Always remember this is addition. This is addition, okay? Yeah, there's some examples. Maybe you can go over. Right? EI plus pi J minus square root 3K. Right? This vector can be written this way as a point. If vector written this way, you always think that's a vector come off the origin. Okay. We can use IJK to represent. What about this? If one component is 0, it's just missing, right? In this case, the I component is missing. So we see the vector just doesn't have I in it. In this case, the vector, right, that's the same one. Vector joins the 2 points, right? This shows you if we are given 2 points, we can always make them a vector. Then depends on only the arrow, right? Depends on who is the initial one, who is the end one. When we write the first point first, we indicate that's the initial one. This is given your vectors, you add them or scalar multiply them. Draw the picture of this. Sometimes in 3 dimensions it's quite difficult to draw. Okay. So equation of lines. Actually, I'm going over. Okay, we're gonna go over this next time. So before we use y equals to mx plus b to represent a line, right? That's for two-dimensional world. But now, because n, we're talking about n space, so the vector flowing in space, you know, in n space. So how are we going to represent a line in n space? We're going to use the idea of vectors. So if you like, you can go ahead and read this part, right? Okay, all right, so I'm not going to take any more of your time. I see you tomorrow, your time, afternoon, my time, morning, all right? Anyone has any questions? Okay, some people already left. Gregory, I don't blame them because I went overtime.
Hi, Professor.
Go ahead. Yes?
Can you hear me? Right.
Perfectly.
Is there a class on Monday? I don't think there's any class on Fridays.
No, no Friday class, Monday through Thursday.
Okay, great. Thanks. Okay.
You're welcome.
Bye, Professor.
Okay. We have class tomorrow. Oh no, what's tomorrow? Oh, sorry, my bad. Somehow I thought today's Monday. Yeah, somehow I thought today's Monday.
It's okay. I will let them know.
Okay, thank you.
No problem. Thanks, Professor.
You're welcome. Stop recording.